Welcome to another episode, Data with Nick the Greek. Today we're gonna follow up a little bit on the partitions topic based on Coalesce, also having a look again how partitions are working, how we can optimize the execution time using Coalesce, and also see how it's performing, where can do mistakes using it, how we can use it to optimize your performance. And this time I pre-executed our test to avoid us waiting a little bit, because we're gonna work with some bigger data sets today. And as always, we start, of course, setting up our Spark partition. Important Spark session. Important is that we have 4 cores configured, and we have our test data sets, which looks like that. And the test function allows us, that already known from the previous episode, to set up the number of rows, but also number of partitions the data frame should have initially. All right, before we're looking into Coalesce, I also summarized here for reading later on what are the main factors to know. We're gonna create a data set today, which is, I was even going to execute it, 2 billion of rows. And you can see, despite the number of rows, we have 4 partitions. We see that the count also proves that we have 2 billion of rows executed, and we have the uniform distribution of 500 million rows per partition in this case. And we're executing our loop right later on for the Spark UI to analyze also how the baseline behaves performance-wise. So now the interesting part is, if you do a Coalesce on a data frame, we can only go down in the partition size. Also here, adding the link where you can see, didn't pop up. Let's try again. So where you can see the description, how Coalesce works, and also the parameter number of partitions is actually the only one which is accepted. So coming back to the codes, we can see, okay, we can do Coalesce 3, we can do Coalesce 2. It just reduces the partition size. If you want to increase it, you're gonna realize, because I already mentioned, you can only decrease it, that it basically doesn't do anything. So if you write 16 or 12, whatever is bigger than the initial partition size, it just ignores it and returns the already available partition size of 4 of the original data set. What we're doing next is we're looking a little bit on the distribution of the data set. So how is Coalesce working? And the important thing is to know it's a narrow transformation, which means when we're looking on the distribution, and now I did the mistake of executing the job. So if we're looking on the distribution, we see that it basically tries with the available partitions to create the number of partitions you want. So in this case, we had 4 with each 500 million. And what it does is it keeps 2 of them, and the other 2 of them have been unioned together to one big partition of 1 million rows. So this redistribution probably takes a little bit time now, but you were able to see that we have 1 million of rows. And then we're gonna run also this loop right on top of this data frame. And then as a third reference, we're also gonna initially directly create a Spark data frame with 3 partitions. And we can see it has 3 partitions, and those 3 stages we're gonna now evaluate a little bit in the Spark UI. So let's close the documentation. Here already open up our baseline. And what we have as well is we have the Coalesce from 4 to 3. And we have the stage where we directly went down, started with 3 partitions. So we can see, okay, let's see what we have here. So I think I need to open also up my baseline. So our baseline is we have a distribution of 500 million each row, highly uniform. Also the execution time is uniform, and we also see that as we have only four cores and four tasks in this case, we can see that the 2.6 minutes also determine the total execution time here. What you can also see is if you're going from 4 to 3 down, Coalesce, you saw it in the data distribution already, you guessed it, it's not very performant. So we have here 4.3 minutes, and the 3 partitions are surprisingly still some okay as the data is distributed. So let's look first of all on the Coalesce. So as we guessed it already, it's not uniform at all. So we have the 2 partitions which are running as tasks quite fast, which have only 500 millions, and then we have 1 million rows. That's a longer task here, which determines also the 4.3 minutes. So that's the one which for the other 2 cores are waiting for. And this is even worse than having 3 partitions and leaving 1 core out, not doing anything, as we have here. And there we just have the determination of the time again based on the longest running partition. So meaning in this scenario where we coalesce down to a number of partitions which is not even divisible by the number of cores, we leave out we leave out 1 core to work, and secondly we create here a totally undistributed, skewed data set, so that we really don't use our resources efficiently. So that's as a first comparison. So now what we're doing is we're gonna take a look how it looks like if we do Coalesce a little bit smarter. So basically what we are doing, first of all, we generate a data set which initially has 8 partitions based on the same number of rows, and then we coalesce it down to 4. So what we know is that definitely the number of rows gonna be distributed here uniformly. So we take our baseline again. We take now the data set with 8 partitions, and then we take the data set with 8 coalesced down to 4. And what we can see here is the coalescing down to 4 takes 3 minutes. Here we have 2.7 minutes with 8 partitions, and the 4 partitions are a little bit faster, but of course using 8 partitions, for instance, is a little bit more safe, because now we already work with quite a huge data set, and I'm actually surprised that with 4 partitions it works still quite well. So that means here we did a smarter move if we would like to coalesce down from 8 to 4. If you're looking into it, so we have here our 8 partitions. You can see that we have 250 million rows of data. 2 tasks took a little bit longer in this case, but overall we at least use all our cores. And well, again, the maximum value determines the execution time. As we do 2 rounds, roughly, you could say it's 2 times 1.4 minutes. It doesn't come exactly as you can see here. We have 2.7. As some tasks already can start working parallel when the other tasks are completed, as you can see here. And then the interesting part gonna be, I cannot work it due to the recording. Let me reopen it one more time. So here's the one where we go down from 8 to 4. So you can see the number of records are distributed uniformly again, just the execution time takes a little bit longer, which depends on this coalesce step, which we have now additionally within our stage, which you can see in the DHE. It's a narrow transformation, but still it needs, of course, a little bit of time additionally. But the execution time additionally is not that bad that really it destroys our execution here. All right, so let's have a look on another experiment. So last time we talked about the inefficiencies of having too many partitions. So in this case, we have 201 partition data set generated. And then let's see if you get such a data set. Now accidentally executed it again. So if you're getting this data set and you coalesce it down to 4, can we improve the performance? So, and this we're gonna check out now. So we go to our jobs again, our baseline of 4 partitions we already have open. Now we open up the 200,001 to 4, and also the 200,001 partitions. And what can already see is a signal is, yes, it looks like it can improve the performance. So we have our 2.6 minutes baseline. We have 4.1 minutes when we have 200,001 partitions. And then if we are coalescing down to 4, we actually get not too far away from the 2.6 minutes. And I mean, it's 25% faster just by having a lower amount of partitions here. So getting to a baseline, we already know it. Then our highly scattered small tasks, which require a lot of scheduler time. So you can also see on purpose I increased it by 1 to have a slightly non-uniform number of rows as well. So you can see that that's highly scattered, and some tasks even need 0.4 seconds, some 2 milliseconds. And then if you are taking a look into here, we again see, okay, the number of records is not 100% distributed, but it's not too bad. It's like 500 records difference to, no, it's actually 8,000 records difference there, but we are talking about 500 millions roughly per partition. So it doesn't look too bad, and you also can see it in the duration. The distribution of the duration is also not significantly different. And by that we are improving our distribution time here. One last experiment, which I did also out of curiosity, because I checked a little bit the data set. It's around 8 gigabyte when I persisted on disk. And I mean, for this amount on 4 cores, I'm surprised that it's even running with 2 gigabytes per partition roughly. You would rather go down to, for instance, 40, so 200 megabytes, or maybe even 80. And you can see here we have also a well-distributed data set. So in this case, we have only 50 million as we have 40 partitions, and the distribution of the execution time is quite nicely. And also looking onto the duration, actually 2.6 minutes, 2.6 minutes, the execution time is equally, then of course I rather choose to avoid any spillover, only overwhelming of my work with 2 big partitions if I'm even able to keep my 2.6 minutes execution time. And with that, that's everything for today regarding coalescing and how you can use it for performance improvement. And thanks a lot for listening. As always, please subscribe to the channel. Please comment if you have any comments, what I could have explained different or what I can still learn. And keep coding. The code gonna be shared, and also play around a little bit with the experiments to really understand how coalescing and the partitions influence your performance when processing data, narrow transformations with Spark.